record to the cloud. Okay, recording has started. Fab Academy Recitation, a really core topic for Fab Labs, sustainability, that we have a great group for on sustainability, agriculture materials. So Marcin, take it away.
Okay, so it's 15 minutes and questions right after the 15 minutes, or is it all at the end?
Interactive, 20 minutes a person. Questions can be at the end. Questions can also be in the chat. They can break in if they're urgent. Go ahead.
Excellent, thank you. Well, we've got a lot to do with sustainability. We talk about, so my name is Marcin from Open Source Ecology. We design and build open source industrial machines, publish the plans on the internet for free. You might have heard about the Global Village construction set. So today what I'll do is I'll talk about a project that we have going on with the Open Building Institute, a project to make affordable housing widely accessible. And how does this relate to housing? Well, part of the structures that we build are aquaponic greenhouses. I'll talk about some of the automation and digital fabrication aspects of that. So I'll do a quick recap of what I talked about last year. You can also watch my TED Talk about the Global Village construction set, 50 different machines. We do have some product releases like the compressed earth block press, 3D printers, now the house. Last time I talked about our printers that are scalable. We use these a lot of modular interchangeable parts like the universal axis, which can be scaled up to large machines like torch tables, or even larger machines like heavy duty machines. And tractors. So this starts to relate to agriculture here, where interchangeable parts can work together. You see construction work. This is some of the latest, not super latest, but recent work. Aquaponic greenhouse, which is the main topic for agriculture. But when we talk about ecology, I also want to just bring up the concept of how we do things with product ecologies, meaning machines building machines, like the Fab Lab concept. So from 3D printers, we make larger parts for the larger axes for torch tables. Torch tables are used to cut steel, like for the brick press or tractor. But then a big question about industrial ecology is how do you return back to feedstocks? And that is through additional product ecologies such as shredders and plastic extruders or induction furnaces, which allow you to either make virgin plastic from waste plastic or virgin metal from steel. So going all the way up to completely cyclic material flows. And we use highly modular build systems of all kinds of interchangeable parts like motor units, power units, where you see that motor unit being used both in wheels or the big trencher here. Here's a smaller tractor, and we talk about construction set approaches. So getting to the aquaponic greenhouse and agriculture, this is the build from 2015, one that was our first experiment in getting a really nice system going. We built another one in 2016, and then we were building another. So what's the news for this time? Right now, about this time, it's time for product release of both the houses and the greenhouses that we're doing. Some of the things that are relevant is moving towards 3D printed components. I mentioned about 3D printers and shredders and implied filament making, but the idea is that if you take the waste plastic stream, we can start building construction materials if we have access to low cost waste stream plastic that allows us to do so at very low cost. So for example, here's an example of double wall this is not polycarbonate, but for example, our the windows in our greenhouses are polycarbonate. Well, you can print with polycarbonate, but here's an example of printing with PLA for the double wall glazing structure. 3D printers are great at applications like that, such as heat retaining glazing. So that's one application of digital fabrication here. So with the larger printers and making of filament from the waste stream, we aim to be able to print not only the glazing, but also even the panelized construction modules that we build. That's a lot of good work that we're working on. And some of the other, we will also include some experimental aspects building on what we already have done with the greenhouse, such as going towards closed loop water systems with worm towers, ozonators, and biological wastewater reclamation. So I'll talk a little bit about that. So for example, here, In this bottom left corner, you see growing towers, which are filled with medium, and we can grow worms in them if you put biological medium in there, or grow plants in them. So this is the general concept, modular design, using the vertical space. There's fish ponds and vertical space. So in a greenhouse like this, you're using 4 feet down on a ponds, and you're going about 8 feet vertical with towers. So that's a big deal, using that vertical space so we can literally get like 10 times the productivity. So this was how we were starting on a build with a glazing. This is some of the
Oops, I don't know if you can hear us. That was great, but you just froze. Okay, recording has restarted. Pick it up.
Excellent. So we've got the tractor here now, the shipment of polycarbonate glazing, which we use to build the structure like this. This is after a 5-day workshop. We did this all with a swarm of about 25 or so people. We do these collaborative swarm builds to do things like this as an immersion education experience for people. And that's what the inside looks like, with 12 feet of vertical space, about 4 feet down into the ponds with aquaponic tilapia. The tilapia provide fertilizer to grow plants in the towers. What you see on the right-hand side is also nursery work, meaning we're actually growing out a bunch of hazelnut plants that are that have been planted out in the field already. This was a few years ago now. So what are that's some more pictures. What are some of the systems in there? It's a whole biological system between fish, worms. There's recycling of nutrients. We had black soldier fly larvae. We have the fish that poo in the water, and that's fertilizer for the plants. And we're taking this further, actually, in that the worm tower, these are green growing towers, but you can also fill the towers up with worm medium. We actually found that in the worm tower, the plant towers themselves, worms would actually get in there through the whole system and take over the space. So we actually have this concept that, well, why not, instead of just the fish fertilizing the plants, what if we actually took it a step further and include a biodigester step, so anaerobic digestion, and then after that, the effluent, which is almost fertilizer, fed through worm towers or worm beds to make this thing work. Now, so yeah, we had a lot of variety in there. Like we also had chickens and mushrooms, but what's the deal about potential for the digital fabrication? So if we talk about, one of the things we found out is planting the towers, we could definitely benefit from some automation. So a system kind of like you might have heard about FarmBot, this common agricultural robot, open source project, using that to seed our trays, which we then plant out in the vertical towers. That would be a good idea to include some digital fabrication or digital automation in the whole program here. Other things we did, we 3D printed, for example, cups that go into the towers that hold the little mass of vermiculite that holds the plants. So that was a useful thing to do for 3D printing. These towers, actually, these are not 3D printed. They're off the shelf. That's just PVC pipe with reticulated foam medium, but you can also 3D print these. And some people have done that and stacked them up. Even if you have a small printer, you can print small sections and then stack them up vertically. Now, the other thing that I want to point out too is in this system, there are some other useful 3D prints that you can do. Like, for example, in a growing shelves for the nuts here, they are growing in trays that's actually watered. That gets watered by the fish water as well. There's actually hydronic heating that's inside the water for the winter so that the fish can get heated and grow faster. But one thing that was really useful with 3D printing is we installed fittings, which were fittings that allowed us to fill the top tray, and then the water would fill the tray, and then at a certain point, it would start spilling to the shelf below. Now, there weren't any commercial fittings that could do that. They're basically like an overflow fitting with a weep hole. So once you stop watering, all the water falls back into the ponds. But while you're watering, the water overflows. So it's a complicated fitting that we needed for this specific purpose that we did with 3D printing. What else is there? So there was hydronics, the fish, mushrooms, and this kind of stuff. So you can see all this on the wiki. We're also installing a control system. So one of the things that's very useful is to automate the watering, because we've actually, by this time, ended up spilling or flooding our ponds several times already because you just forget to turn off the water at some point. So actually one of our ponds has caved in and we're going to have to actually fix that. But automated watering systems can definitely do it. Simple Arduino, solenoids, water solenoids would be a good idea. Here's a picture of this actual complicated fitting that we had to do for the shelves for the nut breeding, and which we then have planted out. And we've seen a lot of different pest management happening, ladybugs, praying mantises feeding on other critters, frogs settled in here, things like that. But the idea there is actually quite ambitious. And if you look at it, maybe I'll finish with that and then go to questions. But the energetics, the idea there was, can we actually feed 2 people a full diet from the biological production of 800 square feet? That's essentially a greenhouse attached to the front of a house. Well, if you do the math, that's 70 kilowatts solar input. Plants convert sunlight at 1%, so you get about 700 watts worth of biological chemical energy. Now, if you talk about the sunlight, the sun shines half the day, so you really have like 300 watts of chemical energy stored. Now, an average human uses about 100 watts of power, so that 350 watts is not going to do it because energy conversion of us eating food, like the fish or the mushrooms or the plants in there, we could only get like 35 watts for out of that greenhouse, unless we actually use some more external feedstocks like chickens, rabbits, fish food. Those are external inputs. Those are not direct input by solar gain. And with that, it turns out the productivity is amazing. We have 3,000 gallons of fish pond, which means 3 pounds of fish per day. So that's actually plenty for a couple of people to live on. Then if you talk about mushrooms, which live on straw, they provide, we got results of 12 pounds of mushrooms over 1 square foot of vertical buckets with mushrooms. So stuff like that. Productivity is actually really amazing. And we found that, yeah, if you do have external inputs like straw or chicken feed, or if you've got fish food, yeah, you can definitely do it, but it's kind of hard if you just depend on the productivity itself. But anyway, so I think I might end at that because I think my time is out. But maybe we can have some questions. I also have this presentation online, so I can send you links.
That's great. Very impressive. So let me start with, I'm really struck by the extent to which you're designing ecosystems. To talk about where does the knowledge come from? How much of this is experiment? How much of this is expertise? How much of this is ancient wisdom?
Oh yeah, good question. Can you hear me? You can still hear me?
Yep.
Okay. The thing is that it's easy to get a system that, I mean, what we have is a prototype still, but we've learned so much, and the point is, it's definitely not available as open source information. You have to really go far. And if anyone actually has a system that works and works really well, it's all proprietary. Like, for example, the towers, we innovated on that. So it was something that we built upon and made it cheaper, better, and faster, stronger. So we actually don't have a comparable model with this level of integration that we know of. I mean, as far as ancient wisdom, it's not, I mean, of course it's ancient wisdom. People have known these kinds of techniques forever, but the question is integration into a whole that actually makes economic sense. And to manage that kind of complexity is a big problem. Like, for example, one thing we learned and in the next iteration we'll solve is just simple things like the water going in the top of the towers. It splashes a little bit and therefore it leaks all over the vertical towers. It ends up causing too much humidity and just spilling, just making a mess in the greenhouse. Like little details, detail after detail that you have to work out, that unfortunately is we could not find anywhere. So it was kind of we had to sweat through it to make it work out, and it ended up working quite well. And we do believe we can get a good commercial operation out of this, and this is our next step.
And then I'm impressed by, and I want to underscore your last few slides. There are lots of DIY agriculture projects that don't account for the inputs versus the outputs.
Yeah.
And the question of what you need for this to be sustainable, it is a really deep, profound one. Have you tried to do a biosphere type estimation of what you would need to close the cycle on the external inputs?
Not specifically, but we know that, I mean, this might sound crazy, but in today's society, we throw down our wastes down the drain, down the toilet, right? But right. I think we can include that and have a system that actually works like that between human waste. And if you simply, like, for example, mow your lawn in the front and make that into growth medium for either worms or pellets for rabbits or fish food or something else, or mushroom stock, you can definitely do it. But no, we don't have enough data on that. But I think the implications are clear that closed loop systems as such, including water, would be good for Mars, and if we got to go anywhere else.
Yeah, no, I think it's a wonderful question. Generally, the experience to date has been the fragility of them, the challenges in making them stable. Any other questions before we go on from anyone?
Yeah.
I'd say,
on the fragility, I think, no, that's a great point. And because we've got so many things in there and we're designing for resilience, I think you can do it, but you just have to put in a lot of different elements that are typically segregated, and that's a hard part.
Okay, you'll find lots of overlaps with the three people. So we'll be posting each of these. Thank you, Marcin. Alicia, take over.
Great, thank you very much. I'm going to just share my screen now. Okay, can everyone see that all right?
Good, yes.
Okay, great. Thanks for the opportunity of presenting today. I'm really excited to hear feedback and questions. My name is Alicia Garmalevich. I'm a professor of circular economy at the University of Santiago in Chile, as well as founder and director of Materium. And Materium is an open platform for biomaterials development and open data. So what I'm going to present to you here is definitely a work in progress from the perspective of community building and the vision that we're intending to develop. So to launch into it, the inspiration really behind Materium is the natural world. So understanding that for billions of years, terrestrial and marine habitats have thrived in producing vast quantities of materials, all without landfill or waste. So the idea is to take notes from that. And in terms of enabling a different approach to supply chain development with these new materials, our goal is to participate, to enable everyone everywhere to participate in these next generation of materials that are actually regenerative, so come from biomass and go back into nutrients. To give you a little setting of the scene, we look at the abundance of biopolymers in the global biosphere as inspiration for developing bio-based materials. Specifically, if you look at the comparison in the volume of biopolymers like chitin, hemicellulose, lignin, these are all components, hemicellulose and lignin components of plant matter, chitin, a key biopolymer in crustaceans and fungi. You see orders of magnitude more in terms of the actual annual production of plastics, which is around 360 some odd million tons at the moment. Plastics production since 1950 is only 8 billion tons. And in comparison, we've got chitin around 100 billion tons in terms of annual production in the biosphere. And so you see it dwarfs actual human production. However, obviously these materials that we're producing, petrochemical plastics and their derivatives, are all accumulating in the global biosphere and causing acute challenges such as microplastics in our drinking water, including in the human system as well, accumulating in tissues, etc. And then of course in other marine and terrestrial life. So it's an acute problem, but we need to look at the natural world in terms of the kind of solutions that we can create from a materials perspective. This is just a quick show of cellulose can't even be shown on the same graph without making the others seem so minuscule. So cellulose is the major component of plant matter, and you can see it's just 2 teratons in volume. It's just incredibly abundant in the global biosphere. So we like to look at this kind of paint box of material components and look at how we can compose our material world and generate recipes that can incentivize people everywhere to start making and commercializing materials with these same building blocks, and using life-friendly chemistry methods as well that ensure that biodegradation happens after end of life. So to that end, we're building an open source database of materials, and I'm going to just quickly jump out of this to show you where we're at right now, which is an open recipe library of biomaterials that's community generated. So this is updating all the time with various contributions, but for example, you can jump into one of these recipes and you can see it's the composition of the materials. These are all screened for being regenerative in terms of their potential to be sourced from sources of biomass that are abundant, and then using chemistry methods that again ensure biodegradability and return of nutrients after end of life. And so the idea here is to provide this kind of layer of information to help more people in more places commercialize and experiment with materials that are fundamentally regenerative and can use ingredients that are around them, specifically in their local environment. The great thing about biopolymers, the ones that I showed you on those graphs, is that even though there's a select amount that the natural world builds again and again with, they're found in different locations all over the world, that it means that you can pretty much source and fork a lot of these recipes and adapt it to your local sources of biomass. So that's where we're at the moment. And I'm going to introduce today a little bit more of the larger vision around data that we're working on right now. But to go back to the presentation briefly, the key with this biomass sourcing is that although it's very abundant on a global level, on a regional level, it's quite idiosyncratic and distributed in terms of where this biomass is found. And so aggregating it and into a centralized production system doesn't make much sense. This is a graph just showing food waste as an actually really important underutilized source of biomass, but it's very distributed, obviously, with population all over the world. And looking at harnessing that into making plastics, for instance, is something that we think that can be harnessed with a global community. In broad strokes, the idea is to move from a centralized production system, which is what we have today, where by and large, finite petrochemical resources are mined from the ground and then made into products and distributed through globalized supply chains, to a distributed and regenerative system whereby materials and the supply networks that make them are regionally oriented in terms of materials and products are made in more globally distributed networks. And then after end of life, those materials are actually designed to be put back into those source ecosystems to regenerate them. And in terms of moving to that world, what we're trying to provide is a data commons that will basically be irrigation for that transformation. So the idea being is that if you're an innovator anywhere on the planet and you want to get into the materials development game, you'll be able to get started a lot faster. Your R&D costs will be a lot lower. And the idea of this world as well is integrating very strongly with emerging networks around local and regional production that are being spurred on by digital fabrication, et cetera. And so that's the transition that we're aiming to be part of and enable. You see companies and innovators starting to work with commercializing some of these materials as well. So for example, ecovative design is really emblematic on the package. I'm focusing here on packaging, but it goes beyond packaging. In terms of mycelium or fungi-based materials, Marinatex is using fish waste primarily. Sway is abundant sources of algae that are grown in California in this case, and Biome is a construction company actually for insulation and wall panelings, et cetera, that use food waste as well as mycelium. So now I'm going to transition briefly into the kind of future of Materium, of what we're building now. This is a skin of what the future system will look like. But basically the idea is to show you here that we're starting to integrate the properties of those materials, because although you can search for the recipes and understand how to make them, etc., what's missing is understanding their performance and how they could compare with current materials on the market. And that's super important both for guiding future development, i.e. tweaking the recipe to make it more high performance in one dimension or another, as well as saying this is a better material or as comparable to a material that's, you know, polluting and we want to replace. So this is an example of the type of system we're building. This is a real data set that we've developed in Santiago. These are variations on one material recipe. So this is an agar bioplastic. Agar is from red seaweed. It's a kind of bioplastic film that you can use for numerous types of packaging. And we varied systematically the ingredient components so that you could get different properties. So here you see a schematic of the various components. This is agar, glycerin, and water. So an incredibly simple material system. And when you can browse over, you can see the actual mechanical properties come up on the right in terms of the yield strength, elongation at break, etc. Now, the idea of our system that we're building is you'll be able to add it to your own personal sandbox of material data, so you can compare properties with other materials. So here's an Ashby diagram where you can look at, for example, Young's modulus, ultimate tensile strength on a graph. And again, you can see your points laid out. The goal of this is to integrate other material systems into this so you can compare and contrast. And we're also looking at other types of data visualization, which will help in the materials development process. So not only the kind of final material properties, but also, for example, understanding viscosity of a material, printability, 3D printability, et cetera, other process parameters that can help optimize a certain material for your intended manufacturing process, as well as your performance outcomes for an application of interest. So that's a little peek at what we're building. Back to the...
Sorry, Alicia, a question at that point. Stephen is asking about carbon footprint. To what extent these materials are carbon sources versus sinks and life cycle carbon?
Sure, that's a great question. So I'll just go back to this slide actually, because we've done some initial analysis on that. It really depends. So on the left, you see two LCA comparisons of biopolymers versus the
Sorry, explain LCA.
Sorry, life cycle analysis, which basically takes various environmental indicators, including climate change impact, as well as, for example, other indicators like eutrophication, as well as human health impacts, a basket of different types of environmental and social impacts often, and then ranks materials, or you can actually compare and contrast them on those various indicators. And so it's over the life cycle of the production. So from their actual origins, their chemical synthesis, right the way through to an intended life cycle. If you look at climate change impact in terms of some of the feedstocks that of interest here, on the top left, you see low density polyethylene compared to polylactic acid, PLA, from primary biomass compared to, that should read PHA, which is a new type of bioplastic that is bacteria derived. that should be PHA from primary biomass rather than PLA. Then you can look at PHA, the same actual material, but from food waste diverted from landfill. And you can see on the graph here that the PHA from food waste is massively carbon negative compared to the carbon positive, or at least climate change impact that you see from primary biomass as well as LDPE. The point here is that bioplastics alone, if they're using primary feedstock, and that means like corn, soy, etc., that are usually monocropped and in today's commodity markets, that can be as or more even climate impacting in terms of carbon emissions compared to petroleum feedstock. And so you get, that comes from land use change emissions, it comes from basically a bunch of the inputs that go into the actual crop production itself. And so we don't want to just supplant or switch out petroleum plastics for plastics made from primary biomass, because you get competition for arable land for food and a bunch of things. So what we're looking at is more distributed sources of biomass, and one of those is secondary sources like unavoidable food waste, agricultural byproducts, etc. And some sources like seaweed, etc., can be carbon sinks, and they can require quite minimal inputs as well. So seaweed farming is an interesting growth area from a materials perspective. So we're looking carefully at that, but it really depends on a case-by-case basis, I would say. And you really need to look at your source and your supply chain in terms of where that biomass is coming from and how it's grown in the first place. Hopefully that answers a little bit. So back to the kind of the data infrastructure that we're building, there's two main technical components of Materium that is going to enable, we're hoping, a large amount of data on biomaterials and their applications and properties to be available and freely available in an open source manner. The first is an autonomous materials platform that's being developed in partnership. And so that actually integrates digitally fabricated technology for materials measurement. This is ongoing work in collaboration with CVA, which is actually developing a lot of these technologies. And the idea there is to integrate these digital fabrication technologies that are measuring the materials properties as they're, for example, a 3D printer that measures rheology of the material as it's printing, or universal testing machines that can be integrated into the workflow of a material that is being produced, so you can understand the tensile strength of coupons and then continue to optimize that material as you go. This is the kind of low-cost open source technology that we want to help decentralize and disseminate through the Fab Lab network. And the idea there is to be able to make materials in a much more data intelligent way. And the other part of that integration is integrating machine learning into that loop of materials development, so that, for instance, you can use technologies such as active learning, which take the data from an experimental workflow and then give you a prediction of what experiments you should do next if you're going to optimize, for example, that material for a given application, or explore a design space a lot more broadly. And so those machine learning tools can actually provide intelligence to the material developer as they're going, and then that can better optimize the experiments that are done. And so
Alicia, sorry, just for time, let me interrupt, keeping an eye on the time. Marcin has a question, and I have a related question. He's asking about open source bioplastics. Marcin, essentially everything Alicia is talking about to some degree is open source bioplastics, but it leads to my question, which is there's some proprietary successes of biomaterials. Mm-hmm. I don't yet know a killer app home run for open biomaterials yet. The question is, as you know, I'm a big fan of this whole roadmap. Where are the early wins going to be?
It's a good question. I think that the early wins are going to be less in a kind of silver bullet material that gets, say, mass manufactured, and rather materials in, for example, packaging that can be made easily everywhere. And so we're talking about more regional markets for food and produce that can be easily, these materials can be easily replicated. So, you know, from gelatin or starch or algae, etc. These are the materials that can be made at a very low cost, small scale, but can be replicated massively. Like the horizontal scaling is huge potential. So I don't see so much a commercial silver bullet that's going to sort of take over the world, but I do see a kind of very quick replication of a certain set of recipes that are easy to do. The other thing to mention on the IP side, though, is that this is not in tension with IP necessarily, because if you want to take one of these recipes and adapt it for specific process, like process manufacturing that you have, or develop it and optimize it for a specific application, that can be commercially patentable. Like that's not an issue. The idea is that you're basically allowing more people the chance to get into that game. And so it's not necessarily the case that open source has to be in conflict in that sense. It's providing that data layer to get people going in the first place.
What about material feedstocks in Fab Labs? If a Fab Lab wanted to start replacing its inventory, where would you direct them?
Yeah, so that's actually a live question right now, which it would be great if people are interested in working together on that. So we have a current project going on, for instance, in the south of Chile that's just got funded to look at using the Fab Lab Austral, which is the southernmost Fab Lab in the world in Puerto Williams, using crustacean waste to make chitosan materials for packaging and construction, etc. And so we're looking at the numerous types of materials you can make for that Fab Lab, but starting from the feedstock that's available.
Oh, so yeah. So let's see. Jens in machine building has a great picture where he shows the parts he has to buy for his machines versus the part he makes. And each time the picture moves over a little bit. In the same way, I'd love to see an exercise to take the Fab Lab inventory and then just show, you know, bit by bit how much of it you can displace.
I would love that too. And that's actually something that it would be really brilliant if anyone would like to partner on that, specifically with Fab Labs who want to trial out some materials, because I would say we have a lot of starting points, but we need to actually optimize a lot of these recipes for the types of materials that are specifically of use in Fab Labs. So that's a project that would be excellent to work together on if anyone's interested in.
Yeah, I would say Nicole's signing up. I would underscore there's the Valdora Green Fab Lab, Blair's lab in Idlewild. There may be there's a Bhutan lab. There may be emerging this sort of network of aiming to be off-grid labs.
Perfect.
To really try to organize as a working group.
I'd love to do that, and we could definitely focus on that in the year ahead. So yes, let's follow up on that for sure.
Very interesting. Okay, for time you have to go on. Thank you, Alicia. If you can stop, a number of people are signing up to work with you on that. And then finally, Luke, if you can take over.
Yes, I've put my video background so you can see AgriLab, and so you will see more rural place. And I'm taking the screen now. So just to give a bit of context on agriculture. So agriculture is really ancient.
Sorry, Luke, that's a little small. If you can increase the zoom in your browser.
Yes, is it better?
Yeah, that's easier.
So it's a long history, and it's really difficult to compare agriculture because it's different everywhere. It's based on geography, climate, economy, and culture. So this is a picture in Vietnam, and this is a more classical way of doing farming in America. It's more industrial farming. This is some kind of cliche of permaculture, French farm, really different with a lot of polyculture. This is mostly how milking is done. It's really, this is called the 1000 cow farm. And this is what most people have in mind when they are buying a bottle of milk. But those really exist also in France. So this is really different situation. Just to point out, there is a open agriculture project that has been running for several years in MIT, and this was called the Food Computer. They also try city farm. So I talk mostly of urban and rural agriculture. They are not opposed, but this is the kind of results you get when you are looking in a search service for smart gardening. So this is a certain kind of picture. So I did some kind of those projects when I started Fab Lab 10 years ago. So I did mostly urban farming. It works well, but you can say for sustainability, there are some kind of scaling problem. You need to add light, you need to add heat and water. On the other side, rural farming is not perfect neither. Intensive agriculture tends to produce monoculture. You have to buy extremely expensive tools like huge tractor, and monoculture creates unbalance in the ecosystem. You exhaust the soil of nutrients, and so you have more risk of disease and pests, and you have always to work the soil or to add chemical. So I think previously you have somebody talk about farm bots. This is generally what is shown with agriculture. And here I take the Excel version. So it costs about $4,000 for 18 square meter. And this is not realistic for economy in agriculture, like a basil cost less than $1. So this is not realistic. Also, there is the idea that if it's farm in the nearby, it pollutes less. This is not also always true. This is a farm in France growing tomatoes, and they emit really a lot of light during the night, and it's really perturb all the ecosystems. So it has a huge impact. So sometimes to buy foods from far away is more sustainable than to buy food just next to you. Those are examples in Brussels of big scale urban farming. So urban farming can be sustainable on a huge scale. So this is example. Here, for example, they take the heat from a rooftop to grow, and they combine the growing of fish, greenhouse, and more traditional farming. But you cannot find all those places. You cannot multiply it. It's really certain points. So what are we talking about rural agriculture? So I said it's climate dependent. You have, when you prototype, you have to see on 1 year scale. Impact on ecosystem are not easy to discover. It can take several years. I talk a bit about the size. So if you grow one basil, it's not the same as to have a personal food garden. It's not the same as greenhouse, and it's extremely different from crop fields. And when you prototype, you cannot do, you have to think about life form. So animal and plants are life form. On electronics, so in Fab Labs, we try also more to do electronics, and outside there are many problems with extreme temperature variation, light, humidity. Most of the time you have no grid power, you have no communication, and there are many different problems that are really difficult to predict. So those are examples of sensor we built and we put outside, and most of them were destroyed after several years, with taking a lot of anticipation of them. So in agriculture, I want to showcase more some of the stuff we do in AgriLab, our community and technological response distributed. And so we can do precision agriculture. So precision agriculture is to put chemical at certain place and not everywhere. So you can do that with certain maps. So like here, you don't use the full ramp, you do it selectively. But for this, you need expensive tractors that are not really repairable. And so with those, you can really have more efficient way. And I think my colleague Florent is online and he can maybe explain more about the self-driving tractor. Florent, are you connected?
Yes, I'm here. Maybe you can just, okay. So you can see and hear me?
Yes, audio and video are good.
Okay, so I'm Florent Lemaire, I'm working at AgriLab, and today I will show you one of our projects we build with farmer. So it's a project to retrofit 99 computer and add precision positioning system in it. So we have some 3D printed part, the gear here to control the steering wheel, the motor and the support here. We have the computer with the software to drive the tractor. We have some electronics here, Arduino Nano and compass, analog to digital converter, DC motor driver, and at the outside. So you can see I'm in the field. We very weather dependent. It's not sunny today. So we can see here on the tractor we have a steering angle sensor to check where the wheels are going, because in some tractor with the hydraulic steering system, the steering wheel drift a little, and you can have a you haven't a direct connection between the steering wheel and the wheels. So the middle position of the steering wheel is not always the same. So we need to have a sensor directly on the wheels to know the correct angle. We have here the GNSS receptor, dual channel receptor to receive the position from the satellite. And now we start the tractor and we show how it auto steer.
So just to add, with this kind of system, you have precision of about 1 to 2 centimeters. So this is extremely precise. You are always in the same position. And it enables to do precise agriculture on really huge scale.
So now we start the tractor. He finds his line, finding his line, and now he's going to follow the word we programmed to test for the demo. We can see it always adjusting all the driving. We have some settings on the system to set a different kind of tractor, the position of the antenna, some settings on the vehicle, and also on the tools, because you can have loaded tools on tools on wheels and the size, so we can set all these parameters. And now we are going to the farm. can see because the real-time kinematic system work with base station that receive with also GNSS antenna the signal from the satellite, but the base station know exactly his position, so he can compute the difference between the position received by the satellite and the correct physical position. With this result, he can send the correction, the position correction to all the rover around to adjust precisely the correct position, and can go down to 1 or 2 centimeter correct position. So here it's still Luc is showing the network of the station, and it's called the project Centipede. And now I will show you. We are just Luc, if you can just stop the sharing. Yes. So I will show you one of the best stations here, directly on the farm. It's this station is connected to the Centipede network, and the farmer can use this position. It works internet, and if you have Wi-Fi or cellular connection, you can get the correction on your tractor. So you can see here this brand new 99 tractor retrofit with auto steer system. Luc, you can continue if you want.
Yeah. So the idea is really to empower the farmer, so they can build themselves the whole network of antenna, and they can build themselves all the systems. So we didn't build, we helped them to build it. So this is really the idea, so they can do their own style of farming, because when you are buying from a commercial, most of the time it's dedicated only to one purpose, and it's not really adapted to your own kind of farming. The same exists for IoT. There are plenty of antenna shared, and anybody can connect to them, and that's good because most of the operators don't cover a rural area. They only cover cities. So with your own network and by sharing to other, you can give access and really build connection for sensors. And there are not that many sensors really adapted to agriculture. So I don't know if I can continue or if time is...
Well, see, Luc, there are about 5 minutes left. Given all the good work you're doing, talk about the hierarchy. There are people working on little systems to grow food in the home, on community scale urban agriculture, large scale farming. How do you see them nesting? It sounds like you were speculating that given the efficiency of rural farming, it may make more sense to weight that. Talk about that hierarchy.
So really to mass produce, you need a large scale and a rural model. And we think that tractors should not be several tons. So the idea to make small tractor, I think, could be more explored. And that could be linked to projects like the FarmBot, where you have high precision multi-tool, and by combining those two ideas, you can do polyculture. And this would solve a lot of problem of monoculture that are done nowadays. This is really, and I make a list of most of the agricultural projects done during Fab Academy. So we can see, so I really quickly scroll down, but this is mostly indoors, aquaponie, vertical, and all that. So this is, of course, a great Fab Academy projects. But if you want deep sustainability, you have to think about outside, because as you can see in my video background, there are plenty of space. It's really huge. So this is difficult because you have really harsh conditions. So it's a lot of work to do. Everything is against you, but this is worth a try.
And then Marcin is asking, the tractor automation, how much did it cost, and is that an open design?
It's open. There is a community, and in material, it's less than 500 euros, but that's really a lot of hours of work. You have to adapt. I didn't show, but like the wheel, each tractor wheels are different. So you cannot just copy paste the model and it will not work. There is, every tractor is unique. It's not really, when it goes out of a factory, every tractor is really different. So you have to adapt many things.
But again, it sounds like you're arguing towards investing in rural agriculture as more efficient than trying to ramp up urban agriculture.
I am not opposing them, but it's different questions and then it's different answers. If you have no rooms, you have to think mostly of vertical and extremely high efficiency. If you are in rural part, you have plenty of space and you have a free energy called sun. You have free water, it's called raining. But you have other problem, of course, and it's a lot of labor. It's not funny to harvest under heavy rain, of course. So with automation, it could be, of course, helps. So I don't oppose strictly the two. It's really different, and I think both can gain. But I've seen that Fab Labs focus more, of course, on urban question, because yeah.
Right, and I think it's a really strong point to think about rapid prototyping meets rural needs in the way you're doing. We're up to 10 o'clock, so 3 very impressive projects. With that, I'm going to stop recording.